one of the surest ways to sort of spur mathematical thinking, divergent thinking, getting students outside of that mindset of just tell me the recipe and I'll do it, right, is to give them open-ended questions, open-ended problems, things that may not have an answer, things that may not even have a well-posed question yet, and just invite students, what do you notice about this thing, and what do you wonder? Right? What are some of your observations, and what are some of the questions that you could pose about it? And so I'd like for us to start with this collection of knots up here on the front table. So we're going to walk past them in just a second, give you a chance to take a look at them really closely. There's 4 of you, and there's 4 knots, so I'm going to assign each one of you one of these. And before we do this little gallery walk, the only rule of this game is do not touch the knots. Not because they're expensive and valuable, but because I hope to make a point out of that not touching of the knots in a minute. So the first exploration is we're going to walk past these knots in just a minute and bring some pencil, paper, and everything with you. Because what I'd like for you to do is to think about what are 3 different ways to represent your knot. In other words, communicate what kind of a knot this is to somebody who can't be here in the classroom with us to see it. Right. So think about 3 totally separate ways to describe, represent what knot it is that you're looking at. And the only rule on that is at least one of those ways should not be just a diagram, just a drawing. Right? So think about some way that's not just a diagram, in addition to a couple other ways to describe what your knot is. All right, so here were the 4 knots that you were given. String's a little bit wavy, but I think each of you kind of looked past that to see what's the actual structure, what makes these knots these knots. And then here's how you represented those knots. The directions I gave you asked you to make sure that at least one of your ways to represent these knots was not a diagram. But each of you did choose a diagram for one of your representations, right? Which I think makes a lot of sense because, as they say, a picture is worth 1,000 words, right? So there's a diagram for each of these. What else do you notice that was similar about the ways that you described these 4 knots? There's some common shapes that came up as themes in what you noticed. And notice that the shapes themselves are fairly simple shapes. Snowman is a pretty simple shape. Pretzel is a pretty simple shape. Glasses and hearts. So there's this common language of using simple shapes embedded within larger structures, right, to describe what these knots look like. Now that we have 12 different representations of knots up on the board, which ones of these representations could we give to somebody outside this room and have them recreate the very same knot that we're looking at here on the table? Okay. Mm-hmm. Are any of these good enough? Mm-hmm. Why not? Pretzel, for example, this one, right down here. Pretzel by itself as a designation. That's not super specific. I mean, I've been to enough mall pretzel shops to know what a pretzel roughly looks like, and that stuff is kryptonite, man. It's so good. They hit that like fat and salt. Anyway, but pretzels, even pretzels can look different. Like the pretzels you get in the supermarket versus the pretzels you get at the pretzel stand in the mall. If you look, there's actually an extra little twist in the middle for the mall ones, usually because they try to make them really big, and in order to make them hold together, they need a little bit more structural rigidity, right? So if I were to draw a diagram of what a pretzel looks like, maybe I'll try and do that just up here on a blank screen here. I might draw, for the pretzels I get in the grocery store, something like this. Actually, no, man, that might be the mall one because it's got this little extra twist here in the middle, right there, right? Versus the ones you might get in the grocery store are usually just kind of that, right? And so just saying the word pretzel, I could come up with either of those 2 diagrams, and, well, let's convince ourselves, are we sure that those are 2 different knots? Well, they're not really knots because they don't close in on themselves, but are those really different diagrams? Well, it seems like they should be, but how do we make that intuition precise?
I feel like we need to develop some type of vocabulary to talk about all of the intersections of things, like a loop versus something just like laid over and going through versus not.
Gotcha. Even when we have a diagram, the diagram by itself is not necessarily diagnostic enough. We want to be able to be specific. For example, looking at this first diagram of K1 up here, where it's got kind of a glasses and ears thing going on. It seems like it might make a difference if one of these strands right here is going over the other when it crosses or under, right? So it feels like we might need a little bit more information, even in these well-drawn diagrams, about when one strand crosses another strand, which crosses over and which crosses under. That seems like it would add value to these diagrams, right? And hopefully help us to come up with a representation that will allow someone outside the room to reproduce our knot. Also, that level of specificity would help for some of these other descriptions too. Like when we say pretzel, this description down here for K4 is pretzel with 4 open holes. That seems like it's a little bit more, somebody given that sentence is going to give us a lot closer knot than somebody just given the word pretzel, right? So yeah, one of our goals today will be to develop a little bit more of that vocabulary to add specificity to some of these representations. Let me latch onto that for a minute. With the idea that maybe in our diagrams we should indicate which strand crosses over and which strand crosses under, let's revisit your 4 diagrams up here and see if you can make them more specific, more diagnostic. So take a minute or two, go back to your knot on the table, and figure out how to revise these diagrams in a way that's going to add that extra information about which crosses over, which crosses under. So we decided we needed a little bit of extra information on our diagrams to indicate which, when there is a crossing, and we're going to use the word crossing for this phenomenon, where 2 strands in our diagram cross one another, we decided it's going to be important for us to know which strand is crossing over, which strand is crossing under. So you did that in a couple of ways. For knots 1 and 2, you thickened up your rope here so that you can more easily kind of depict which one is laying over which one and which one is underneath. And for 3 and 4, instead you introduced some simple notation on top of your existing crossings diagram. Can you tell me a little bit about how these little arrows work? Sam, how are you using the arrows in your picture? So here you're using these arrows to indicate that in the direction of the arrows is the over strand?
Yes.
Okay, gotcha. So if we add that information into our diagrams, now is this diagram enough for somebody to recreate this knot if you hand them that diagram? I think it's certainly better than it was, right? Are there any potential complications? Is there anything that would make it impossible, given one of these diagrams, for somebody to recreate the knot that we have? Is there any, maybe I'll ask it this way, taking a look at what's on the screen for a minute. What's an important difference between the knot that John sketched here in K2 versus the knot that we actually see on the table here is K2? Because they don't look exactly the same. What's different?
K2 is a little bit.
So the difference we're seeing is that we can more easily see the structure of K2 in this diagram because there's more space in between the crossings and the strands, and some of the crossings are kind of crowded over here. So one of the things that we all need to decide, we need to decide that that is a feature that doesn't matter in our diagrams, right? No matter how big we draw a loop or something like that, it doesn't matter if we draw it big, if we draw it small, if we draw the strands closer together, further away, that what matters are the what? Crossings. What matters are the crossings. As long as we both draw a diagram that has the same crossings, oriented in the same way, over versus under, and appearing in the same order, that ought to, we think, be enough to classify that knot. In other words, if I give somebody that diagram with the same crossings in the same order and the same orientation, and that I make a knot that meets that criterion, and they make a knot that meets that criterion, that we are both making essentially the same knot. Even if I might do it out of dental floss, they might do it out of rigging rope or something like that, that doesn't matter. How big the knot is doesn't matter. The shape of the loops themselves doesn't matter. How far apart the strands are doesn't matter. The only thing that matters are those crossings. Right? So that's our hunch, that somehow of the methods that you use to represent knots in this opening exercise, it's these diagrams that are the most faithful to what the actual structure of the knot is. Right? They tell us way more than the other ways of representing do. And before we move on off of this picture, I also want to come back to this question that we put in the parking lot just a minute ago about numbers of crossings. So I'd asked you at one point, which of these knots do you think is the most complicated? And the consensus was this one, K3. And the reason that K3 was so complicated is if you go through and you count just how many crossings there are in K3, I'm going to try and do this on the screen here. There's 1 up there, 2, 3, 4, 5, 6. I'm counting 6. Do we have more?
Which is actually the same amount as K1.
Which is actually the same amount as K1.
And K2.
And K2. So all three of these knots have 6 crossings. That's interesting. Are they the same knots as one another?
I don't think so.
That's a good question. We're going to get into that. K4 has only 3 crossings, I think, right? Does that mean that K4 is different knot than some of our 6 crossing knots?
I think it depends on the type of crossing, wouldn't it?
Okay. How?
Well,
so you started your observation by looking at this sort of loop over here in K2 and saying, well, this is not really an important pair of crossings for this knot. So let's call that one not intense. What's the opposite of intense? Dull.
Yeah.
Call that one a dull crossing. Like it's not really important to what the knot is. Right? Whereas the crossing that you were pinpointing over here, this one, there maybe this pair of crossings over there is somehow much different, right? Because it goes over a strand and then it goes under the same strand.
An over-under versus an over-over.
Yeah, so this one's intense, right? Versus an over-over, which is dull. So what we might, if our goal is to ultimately come up with a way to characterize the essential nature of a knot, we're going to need to develop some way of just forgetting about all of the dull sets of crossings, right? We want to get rid of those because they're probably not important to what the knot actually is. Whereas the intense crossings, we want those to be the ones that we hang on to. And so if I give somebody a drawing of a knot where I've thrown away all of my dull crossings, they should still produce the same knot for me as the one that has all the dull crossings in it. So this leads me to this is the first instance that I want to sort of pick up. The lesson is different diagrams can describe the same knot. If we all agree that we can throw away the dull crossings and still have the same knot, that means that we can fundamentally change the drawing, the diagram, and yet still be describing the same knot. So representations, any place that we see them in mathematics, representations are not always what we call faithful representations. It's not always true that the same object has the same representation and vice versa. That different diagrams can in fact give us the same knot. Didn't leave myself much room to write. Can give the same knot. Of course, we're going to have to decide what we mean by same. Right? I think it's easier to describe what we mean by different diagrams. Maybe it has different numbers of crossings. Maybe it has different orientation on some crossing. Maybe it has different order in which crossings appear, right? Talking about what it means for diagrams to be different is fairly straightforward. But, John, your observation is if we just take this green loop over here and we just pull it to the left a little bit, right, so that's no longer crossing that other strand because it's an over-over, somehow we have not changed the fundamental reality, definition, classification of what that knot is. We've changed the diagram, but we haven't changed the knot. And our goal as mathematicians is to figure out what is the essential nature. If you think about it like fractions, what are the lowest terms? What's the lowest terms diagram for a knot that we can draw, right? Different fractions can represent the same rational number. That's another representational problem. And it's probably the source of a lot of students' frustration over fractions when they're learning it in the first place. We could imagine assigning one of these knot diagrams to somebody and saying, simplify this diagram. Right? Try to reduce the number of crossings as much as possible on this diagram while not changing the fundamental identity of this knot. If you're allowed to touch these knots, you could actually do it physically. Right? Reduce this diagram into its lowest terms. That's not the terms that a knot theorist would use, but hey, that's one of our first real analogies, right? It's that idea that some representations are more complex than others. If we can reduce the crossing number, the number of crossings in one of these diagrams, I shouldn't use crossing number, that's something different. If we can reduce the number of crossings in a diagram, then we've somehow gotten closer to identifying at its heart what is the real identity of a knot. I think, though, that the number of crossings is not very diagnostic because we can't really tell until we might have a set of rules for what are the dull crossings and how do we get rid of them. We can't really tell which of these knots are the same as one another, which are different. Having the same number of crossings doesn't necessarily mean we have the same knot. Having different numbers of crossings doesn't necessarily mean we have different knots, right? So it's a piece of information, but it doesn't get at the underlying structure of what a knot is. And so we want to get there somehow.